So, good morning, everyone. If you're wondering whether it is better to install three momentum wheels on board of a satellite system which has a mission to orbit the moon, just for instance, or it is better to put two reaction wheels with a magnetotorquer. So, welcome to my master thesis presentation, which will automate the evaluation of satellite system architecture. So at the end, we'll have an answer to that, what the capability of these tools. This work has been done during my 4 months internship at Interdisciplinary Center for Security, Reliability, and Trust, or SNT, at the University of Luxembourg. I work under the supervision of Dr. Maxim Kordi as a research scientist and Dr. Sami Lazrek as a postdoctoral researchers. This presentation will be organized into five main parts. The first, we come to the introductions, then we continue with the methodologies that will be used during this research and the implementation, and some explanation will be in the results and discussion. Then we continue with the research direction and conclude it at the end. For the background of this research, I will present you two interesting facts. The first, that space sector has become the national research priority, like listed in the documents by the Luxembourg government. And the second fact is actually more than 60 space companies that establish Luxembourg as a country as a European space values. But then one big question arises, how those actors collaborate effectively. So if you can imagine, there are 60 actors working on the space domain, but there is one mission by the government to accomplish. Then how those actors organize their work all together so they can achieve one common goal. Then the answer is high-level strategic planning in early design phase is required. But how then to achieve that? We formulate a lower level question that becomes our research question. The first is how to automate the conceptual and the preliminary design process, which is in the early design phase of a complex engineering system. In this case, of course, we implement that into a multidisciplinary satellite system. Uh, then there are two aspects that we need to really answer. The first is how to explore possible design space of satellite architectures. In this case, we have ranges of components variabilities and subsystem variabilities. But how to explore that so we can have a less bias by the expertise, by the subjectivity of decision makers. Then the second, how to evaluate and find the optimal design of the satellites. Of course, we should know how these important decisions at early design phases will perform at the end after the detailed design. So it is better to have the design evaluation as early as possible. Then once we have the problems in the big box denoted by the number 1, 2, and 3 on the left box, then that will be addressed by the contribution of this research, which in brief, in one sentence, is to develop an automated and unified satellite design tool, which consists of three aspects. So we develop first an architecture modeler and generator. Of course, we're not developing that from the real scratch, but we develop a subsystem model of a satellite using these tools. Then the second, we should have an architecture evaluators. That's why we formulate the MDO problem in OpenMDO for our specific case. And then for the third, we have and need to develop an architecture translator. So those are the aspects that we developed during this thesis. But how these contributions works together, as we already observed in the slides before, that there are three main aspects in the box of blue, which is architecture's modeler and generator, and then box in the red for the architecture translator, and at the end we have a box in green as an architecture evaluator. First, we need to have the ADHG of a subsystem, the design space model of the subsystem that need to be modeled in this research. Then once we have generated architectures, then it needs to be translated in order to be able to work in the architecture evaluators. That's why we need the CFE as an architecture translator. I will explain one by one all the methodologies after this. So once we have all sizing models, the evaluation models, and some components that has been translated from the architecture generator, then the MDO problem can be run using architecture evaluator for sure. Then at the end of the process, we should know the output metrics, which the certain architectures position compared to the others, how they perform compared to the other architectures. So we should know by the end of this process. But it's not stopped in here. Then this result will be translated again into the generated architectures by using the same architecture translator. So the link works in two ways, from generator to evaluator and vice versa. So at the end, we have the complete architectures with their specification, with their characteristics, as well as the numerical output metrics. Then for the first methodologies, we have ADSG. This is architecture design space graph, a technique which represent an elements that will be able to make decision making. So we use a door, which inside that embedded ADSG. These tools developed by the German Aerospace Center. We have intense discussion with them to provide support in using these tools, but we develop by ourselves some of the satellites subsystem, like the HG determination and control, then satellite power subsystem, also the communication subsystem, and at the end we have the unified subsystem of all those trees. And it has, of course, the capability to explore design space. Once we have the variabilities, then they will be able to generate a specific architectures, the list of possible architectures that can be generated and explored from our model. Then we should be able to model also the system interactions, then the component exploration, also the quantity of interest declaration. For the second methodologies, we have MDO for architectures evaluation. So let me check first if I record this already or not. No, it's been recording. Okay, so this is perfect. For MDO, we need that for the architecture evaluator. Yes, it has the capability to model the sizing. So that's why we size, in this case, the components of some subsystem that is exists in a satellite. So there are sizing models. Then after we have all those sizing models, they can be selected or they can work together to formulate the MDO problem, which integrates all sizing model within a multiple subsystem. Uh, the first two methodologies will be glued all together using architecture translator. So that's why the title of this thesis, the title of this research is the automated evaluation. So we don't want those two aspects, the evaluator and the explorator, working separately. So to make them, to map one model from the architecture generator to the architecture evaluator, we need one tool called the architecture translator. So we use the CFE. This is a Python library developed by the DLR as well, which enable us to create a link from other to OpenMDO or vice versa. So they are able to instantiate the elements, the quantity of interest of all our variabilities. In this case, of course, the components, momentum wheel, reaction wheel, and any other components. Then we come into the very interesting part of our research. The first, we have the ADHD of a CubeSat. So this is developed specifically for a CubeSat based on some solid resources that we obtain. For example, the Space Mission and Analysis Design book by Wirtz and Larson, and then some other references, even the latest advancement of components by the NASA. It's called the state of the art. Maybe the most possible components to fulfill a function is those components. So in this ADHD, we model from high level functionalities. We start from determining the attitude, for example, for the attitude determination subsystem. Then it can be derived into the lower level functions. Then from that, we can put some variabilities of components as a function fulfillment. So that's why in the system engineering, we know as a function form mapping, the functions is supposed to answer what the system does, and the form, of course, how the system does. It is represented in this ADHG by modeling the functions and also the components. For example, here the function of attitude determination, of course, to sense or to determine the attitude of a satellite. Then what components can fulfill? How do they work together? We have, for example, here the magnetometer, the gyroscope, the horizon sensor, who complement each other to achieve missions. Then, of course, the second one, we have the attitude control. We develop this based on those resources. Like I mentioned before, these tools are able to explore the components, so we can put as large as design variable as possible. Uh, this is one of the capability of the tools. And then the other capabilities is it is able to model the subsystem interactions. So we'll be able to model in the conceptual framework the system of system, not only the system of interest, but we are able to uh, make the model of interaction between those subsystems. Then for the power subsystem, we do the same. We start from the high level into the lower level, and how the components and function interact together are modeled here. I will not explain that in detail, as well as for the component subsystem, for the communication subsystem, and this is how they works. Then after the component exploration for a CubeSat, then we comes into the other interesting part, which is the MDO of a CubeSat. So we model the subsystem here as a components in OpenMDAO. And within the group of components of OpenMDAO, we have the components of a CubeSat. So in a complete, we can expect the outcome of the MDO will be the XDSM, Extended Design Structure Matrix, and also the N2 diagram. The XDSM, we can get some information from there. But first, we should be able to notice the couplings between the disciplines and the optimizers. And here, we coupled the mass of each subsystem and the power consumption of each subsystem, and then fed back into the other subsystem who will use the input variable of those. Then at the end, we have the optimizer. For a specific case here, we're supposed to optimize the size of the ADC subsystem, for example, the radius of momentum wheel, and also the efficiency of power subsystem, efficiency of solar array, let's say. Then at the end, after it is optimized, we should get the optimum value of the power required to minimize the as minimum as possible or to maximize, for example, the data downloaded for a communication subsystem. So this evaluation is able to do that, not only to design, but to set, to get the optimal value of a design. Then we can expect also the numeric design variables. The input values here are taken from the 3U CubeSat with the size of 3U of a cadre to gather the information from the atmosphere. This is a CubeSat research done by the group of scholars at the University of Michigan. When we have here some design variables that we set specifically for these missions, and then the objective is to minimize the total mass of a satellite of a CubeSat. Then these are the selected inputs, and at the end, we can group the output based on their subsystem. So, for example, we have the mass, we have the power consumption, we have the size and dimension of each components. So the goal of this research is to capture, to give the information what this framework, what these tools are capable of, not really going into the detailed values of the numerical values of a specific case or specific MBO problem, but just to demonstrate what these tools are capable of. Then once we have the complete model of that, we need to connect them all together to automate them. So the result of this automation comes from the architecture exploration by ADSC. Like I mentioned in the beginning, we have three subsystems: power, HG determination and control, and also the communication subsystem. How do they work all together? It's quite important to be modeled in ADOR or based on ADSG. Once it is generated, this is given to the architecture evaluator by MDO. So in summary, this is the HDSM that represent the capabilities of these tools. We have only for now ADCS, power subsystem and the communication subsystem, and we have the disciplines to sum up all the power and mass budget so it can be optimized at the end. After that, in the workflow, we can remember that there are output metrics where the main points of the research would be. For example, here we can plot the Pareto front of the list of architectures based on some metrics in the perspective of some metrics. For example, here if we want to know how some architecture performs in terms of the total mass and the data downloaded, but we want to see the variation of power architectures, power configurations, whether it uses solar array, primary battery or a solar array and a secondary battery. We can see how they compare each other in terms of the total mass and the data downloaded. We can discuss this in detail later. For the second plot here, we have the variability of ADC components, how many momentum wheels we use, how many momentum wheel, and with the combination of reaction wheel uses in the specific architectures, and how if it is only reaction wheel, how they perform in terms of the required powers and in terms of the total mass. Of course, we want utopia point, the point which is optimized for all output metrics. For example, for the power consumption, we want to have it as much as possible. I'm sorry, we want to have it as minimum as possible power consumption. So it's located in the left. And for the total mass, we want to minimize it as well. So it is put in the bottom as possible. So the utopia point is here in the left bottom corner of the design space. But of course, it is not happening if we choose this architecture with the reaction wheel, with, with this reaction wheel. So it can minimize the consumption of power, but in terms of masses, it's not that it's not the least. But if we choose this one, we can minimize, we can get the minimum of value of mass, but the power consumption will be as high. So this is a kind of trade-off that will be captured, that will be addressed. So in terms of the decision making, it will make a non-bias. We get some data to explore based on the requirements and constraints. So this is what the tools are supposed to be. In terms of the research direction, of course, this research is not perfect. There are some any possible advancements or to do after this. The first is to implement all 7 subsystems to complete. And once we have the complete model of subsystem, we'll be able to validate to the existing real case. Because without the complete model of them, it's difficult to do the validations. The second one, for now, this research is just in the early design phase, which are on the preliminary and the conceptual design phase. But if we want to move downstream in the design phase, which is maybe in the detailed design, we need the high or medium fidelity of a simulation model. So it would be interesting if we incorporate those higher degree of models into the current model, which only use the mathematical analytical equations to size some components. And at the end, it is also interesting to see how this tool can perform the dynamic model of a satellite operations. So all over the satellite mission, satellite life, we should be able to see how some characteristic, how some properties evolves over the time. For example, the capacity of the battery, how they are decreasing as the time, and after it is charged with the solar array that they get from the sun, then how how well this configuration perform, not only in terms of the static model, but also in the dynamic model. So these 3 uh, research directions are quite interesting to be carried out later. Then we come to the conclusions. There are only 2 short conclusions, but this is a very broad conclusions. So we have been developing a unified and automated evaluation tool for a satellite system architectures that consists of architecture generator, evaluator, and also the translator. And the second one, for each those aspects, generator, evaluator, and translator, we have 3 also subsystem of a CubeSat or of a satellite in general. We have the edge determination and control, power, and the communication subsystem, which are working together to evaluate the architecture. So this is the end of my presentations. There's some references if you are interested to search. Thank you very much.